Ladies and gentlemen, our next speaker is someone I personally met during my Scala years. I think we met in Berlin when he was working for the Lambda, and I remember we talked about free monads at a meetup. So I'm really proud to be able to introduce him now. I will always recognize him as the author of unorthodox specs2 test framework, but also the F library. And these libraries were truly pushing the boundaries of functional programming in Scala. And his living for Haskell started a discussion about brain power drain in the Scala community. So please welcome Eric Torreborre.
Thanks. Thanks, Martin, for the nice introduction. So, yeah, I'm very happy to be here today. Sorry?
Before you start, I want to add one more thing. Eric will be answering all his questions after his talk in the QA room, which I'm sure you have a link to. Page is yours, Eric.
Okay, cool. Thanks. So, yeah, I want to talk about different things today, but let's start with Lambda abstraction. So, when you hear Lambda abstraction, what are we really abstracting over? Okay, what is the abstraction there? And this is how I think about it. Like, if you have a function like this, like compute taxes, it's effectively abstracting over some complicated stuff that's behind. So this function can call many other functions to effectively do its job, like deductions, applied rate, and there's effectively a graph of functions that's hidden from you. You don't have access to that. And in a way, it's a very good thing because you don't get to see all of this complexity. But at the same time, that poses questions of modularity because you have now this big function. And if you want to change any small thing about it, you cannot really do that, right? And as functional programmers, we often pride ourselves of being able to build big functions out of small functions, right? Very effortlessly. And that's very nice. But once you have this big function, you cannot do much about it. You have to use it as it is. So if you want to tweak it, you have to come back to the code. You have to carefully extract the part that you want to change or that you want to be accessible to the user of the function and expose it in the function signature. And this is kind of annoying that you have to do this. And then the next question is, okay, but in that situation, who is going to build the function you're going to pass to the big function, and who is going to even pass the function to the bigger one? So we have a problem of being able to assemble code, but also deassemble and rewire code to adapt that code to some specific situations. And I want to show you a few examples of that situation. And the first example is something that you might not think about in your everyday use of Haskell, is the use of Haskell modules. So there's this very nice example taken from the Coherent website, where they expose the following problem. You want to write a group by function that's going to take a list of elements and group them according to a given predicate. And that group by function should return a map. And so you can code all of this, and it's pretty nice because it's very generic, right? Except that the type of the map you're going to return is very specific because that's the type of map you're importing through your module system. And you're importing a very specific kind of map, one map that requires an OR constraint. And now if you want to implement the same function and return a hash map, because you also have hash maps in Haskell, then you're blocked. You have to rewrite essentially the same function, put that in a different module. So all of a sudden it's not very modular. And the main reason is that Haskell imports are very implementation specific. You import implementations. So there's a nice way out of this problem, which is to use backpack. I mean, that's the reason why backpack was invented in Haskell. So now instead of importing a specific map, you import a signature for a map, like a map interface. And then you can, through your Cabal file, you can say exactly where you want the implementation to come from which package. As long as it conforms to the signature, you will be good. You can even mix and match different implementations in your project. So this is all nice. This is really solving a problem, but at the same time, it's very heavyweight. Look at what we had to do, right? We had to go outside of our language and we had to configure stuff using Cabal, which is not even a programming language, it's a build language, in order to do something that, I mean, should be almost available at your fingertips. So that's kind of annoying that we have to do this just to wire our code. Another very common example of places where we need to wire code is if you do serialization. So if you have a nested data type like conference, date, attendance, person, and all of that, and if you want to encode this as a JSON value and keep a bit of flexibility, you will have to pass some encoders for both date and person, for example. And then all of this recursively for person, you need to pass an encoder for company and so on. And it feels very boilerplatey. So fortunately, there's a nice solution to this problem in Haskell, which is simply to use type classes. So there are type classes, there's a toJSON type class, which you can use. And now you turn to the compiler to do this, to inject that code for you, to find where the instances are and pass them down to every function that needs those instances. And the compiler is very nice because it's effectively doing even more things for you. It can even derive those instances from the generic declaration that you have on your data types. And then you have almost no code to write. It's going to do all this magic wiring for you. And that's really great. But actually, it might not be great all the time, because let's have a look at this library called Hedgehog. So Hedgehog is a library for doing property-based testing. And when it came out, it specifically said, oh, we are not using type classes. And it was like a way to sell the library. So maybe type classes are not the magic bullet we think they are. So we need to discuss about that. And my last example is how we build applications in Haskell. And it's kind of the same problem, right? You want to develop applications based out of different components that you can assemble together. And in general, you also want to be able to replace those components very easily for testing. You want to replace component in an application by a mock, or by a pure implementation, or by a deterministic implementation for time or randomness, for example. It's very important to be able to do that, and to do that really effortlessly, because when you write your test, you don't want to spend all your time rewiring things for a specific context all over the time, all over the place. And the funny thing is that if you look at the Reddit Haskell website, there are so many ways to do it. And every 6 months, someone comes to the mailing list and asks, okay, how do I build applications in Haskell? There are many different patterns. Should I use the MTL way, the reader, tmonad, or whatever, or effect libraries? And so many of those approaches are effectively using type classes. And for the main reason they are using type classes is that type classes are a language feature providing you with some implicit wiring of what you need. So this is something I want to explore today. I want to explore today those wiring techniques, and in particular type classes, and where they come from, why we use them, how they can be both useful and problematic. And then I want also to put a counterpoint to using type classes is, okay, can we avoid using type classes, in particular to build applications in Haskell? Are there alternatives ways to do this, and while still getting some of the nice properties about replacing stuff? And finally, I want to introduce you to something that's completely new, and hinting at maybe the fact that we have a problem here is because we are based on Lambda abstractions and based on the Lambda calculus. And there might be other ways of computing which can help us in there. So let's start with type classes. The type classes dates back from a long time. They were proposed in an email by Phil Waller, not even an academic article, in 1988. And they were specifically designed to solve one problem, which was operator overloading. So you have the plus operator that you would like to use in many different contexts. You would like the plus operator to be able to add ints, floats, doubles, and it should still be the same plus, not plus int or plus double, or that would be very cumbersome to do that. And you want to have your code parameterized just using the plus operator. The other thing that you want to solve in Haskell is how you declare equality between two values of the same type. And there's this very fundamental property that Phil Waller writes in his email, that there's no lambda function which can decide if two terms are equal or not. It's not lambda definable. So for each type we define, we have to specify all over again how values of that type can be equal. And type classes are a very nice solution to this. And it's, in a way, conceptually, it's not even a complex solution, because the idea is that you have, on top of your regular lambda calculus, you have ways to package functions in dictionaries. And the compiler is going to create those package of functions and pass them around where they are needed based on types. So in addition to the regular lambda calculus, you're going to have the notion of dictionaries and some sort of algorithm that's going to guide the resolution and the construction of those dictionaries and passing those dictionaries simply as function parameters. Nothing fancy there. And that solves that problem really well of operator overloading. Unfortunately, that opens new problems. So for example, there's this very big problem, which is a coherence problem. You have a set, which is a purely functional set. It's backed up by a tree where you can put, for each node, you put elements that are lesser than the current node on the left and greater than on the right. So to build that tree, you need an OR constraint. You need to have ways to compare elements. And each time you add an element to the set, you need this OR function to do, this compare function to do this. And it's very important that you use always the same comparison. Otherwise, if you use a different comparison function, you will get possibly duplicates in your set. So that's why it means by being coherent in that context. And the solution to this problem is to declare that the compiler should check that there's only one instance per type and per type class. And that's a very obvious restriction to have. And you would think, yeah, if you do that, it's going to work. It's good. But unfortunately, that creates another problem, which is that if you have only one instance that's allowed, you have to put it somewhere. And it's either going to be defined with the data type, implementing the type class, or with the type class itself. And if you come up as a third-party library author, you want now to implement an instance for a data type in another library and a type class in another library, and you control neither of those, you have to declare this instance in your own code. And that is an orphan instance. So GHC recognized that problem and said, okay, you can still import orphan instances. They are kind of dangerous because now instances that come in scope have a role to play in the resolution algorithm. But at the same time, they solve a real problem, which is how do you do when you have different authors of those libraries? There's also a solution to the orphan instance problem, which is simply to create a new type. So you can take a type that you don't have a control over and wrap it inside a new type, and then that type is yours. So locally, you can declare any kind of instance you want for that type and a given type class. And that's fine. I mean, in some contexts, that can work, but not all the contexts. For example, if you want to serialize the person data type differently, well, you cannot really inject a new person in that nested data types thing, because then conference needs to point to person and not to new person. You will have to do things differently. And this is kind of annoying. And then I must say that the rule about having just one instance per type is actually more complex than this, because types in Haskell are more complex than this. You have types can be parameterized by other types. So if you look at the definition of Haskell 98, you will see that you can only declare instances for types having type variables that are unspecified. They have to be unspecified to be able to declare an instance. And I mean, you might want to be able to specify them to get more expressivity and more flexibility. Because what you might want to have is more like one instance per type configuration. And this is actually possible. So what that means is that GHC is now opening up a bit its instance resolution algorithm by giving you the knobs to be able to do this. And there's one option called flexible instance that you can use to do this. So flexible instances is lifting that restriction and saying, okay, now if you want to fix some of the type parameters, you can do it. And you can actually even do more, because you can even help the resolution algorithm and drive it to some instances that are more desirable than others, with probably some idea of that some of them are more specific than others. And that's nice, because now you have more flexibility all of a sudden. You have more expressivity in how you can specify instances for different combinations of types and type classes. And there are other options you can use to help drive the instance resolution algorithm. One of them, for example, is undecidable instances, where you can tell the compiler, don't worry about making sure you terminate. I know the search is going to terminate. Don't worry about that. Otherwise, the compiler is pretty conservative about what he thinks can terminate or not. So what can we do with this new ability of having flexible instances? One example is given by Chris Penner in one of his blog posts, in how, again, we can test applications by replacing some components. So in order to do this, you can have a test monad that's going to implement all the functions of your applications. And that test monad can be parameterized by some flags at the type level in order to do this. And if you look at one example of this, for example, here you can implement that test monad. You can implement that accesses to your database. So you have functions like get entity, store entity, and you say, okay, now if I use a specific type parameter, I fix it to DB useMap. I'm going to use an in-memory map to implement those operations. And I don't really care about what the CLI implementation is for this instance to work. They are totally independent. So I don't have to provide anything about that CLI implementation. And then you can have another instance that's going to say, I don't care about the database implementation, but I want to fix what's happening for the CLI implementation. And then when you put all of this together, you can say, using type application, you can say, okay, now run this code. And you specify by using type application, you say, okay, now use the database with an in-memory map, use the CLI with a list, and run my code like this and test that everything is okay. And that's a nice way. You see, as you can see, having this option of having flexible instances, it now gives you more expressivity. It gives you more control over the algorithm that's providing by type classes. But of course, you can wonder, is it safe to do so? Is it a stable extension? So someone asked this question on Stack Overflow 8 years ago. And the answer was, hey, go ahead, go for it. It should work. No, there should be no problem with that. And something like 7 years later, in a comment, someone said, oh, well, actually, it's not so safe. You can still shoot yourself in the foot with this extension. So is that right? Yes, I want to show you that, an example of where you can shoot yourself in the foot. So for this, we need to have a type that's parameterized by two other types. So that's the type A. And now you put in one module, you put an instance for the ORD type class, where you're going to fix the type B that you want to use. And you just compare on a specific B data type. And once you have this instance, you're going to insert elements in a set of A's, using the regular insert function on sets. And at this stage, in this B module, everything is fine. Everything is going to work okay. There's only one instance that can work, and everything looks good. But now you do the same in the C module. Now you fix the C type parameter to something very specific. You say, I don't care about B, but you define a different comparison operation. And again, at the level of this module, everything is going fine. No complaints, everything is coherent. But when you put both of those things together, unfortunately, it is possible to insert elements now in the set where you will have duplicate elements. So flexible instances is not a safe extension to the type resolution algorithm, unfortunately. So you might wonder, what is safe? Which of those extensions are safe? So last year, there was a paper at ICFP where people tried to show if it was safe, for example, to use another of those extensions called FlexibleContexts, in addition to superclasses, which is something I didn't talk about. So you can have classes inheriting from classes, type classes in Haskell. And they were able to show a positive result, that the type class resolution algorithm is bringing coherent instances if you have both superclasses and flexible contexts. And that's great. And it was actually really hard to get there. It's like 20 pages of code proofs to be able to establish that result. Unfortunately, if you look at the conclusions, it says something like, actually, we only proved that for a limited subset of Haskell. But because as soon as you have modules, there are more challenges. So we need to do more research in that case to be able to say what's flexible, what's safe and what's not safe in the resolution algorithm. So what that means is that we have a resolution algorithm which we want to be able to tweak in some places to have more flexibility, more expressiveness as users. But at the same time, it's not very well known what's safe and what's not safe with this algorithm. So if we look at other languages and how they're doing it, it's interesting to look what other languages are doing. So for example, Rust. Rust is saying, no, we will not give you any way to tweak the algorithm. No pragmas, no nothing. But it turns out that they still have issues with things like the orphan problem. And they still have complex types. So if you look at the evolution of this algorithm, instance resolution algorithm for Rust, they finally decided to have less restrictive conditions on what was allowed or not, because they had this, again, this orphan issue. So eventually they said, okay, if you have a trait that comes from a different library and a type that comes from a different library, it's okay to provide an implementation if that trait has type parameters and if one of those type parameters is a local type of yours. In that case, it's okay. And that really helped them, in particular with a library called DSL, where they were, that's defining SQL dialects, and then you have SQL backends on the other end, and you want to be able to have third-party people providing new dialects and new implementations for SQL queries. But the weird thing about the restrictions they lifted is that they still impose a very weird syntactic restriction, which is that your local type has to be the first in the list of all the types coming up in a foreign trait. And this is very important, because without this condition, you can have incoherences between your instance declarations. But at the same time, it feels really weird to have syntactic restrictions on something that should be purely semantic. So I feel there's still much more to say about that. And now if we turn to another language like Scala, they took the totally opposite direction of allowing a lot more things to happen. So not only you have complex types in Scala and many, many ways to find out about instances based on the types that are involved in your code, but also you have different scopes that can be considered. So you have imports, you have local declarations, you have things you inherit from extending a given trait, and so on and so forth. So in a way, this is, again, really great because you have lots of expressivity, lots of different ways to layer your implicits and kind of control how they are going to trigger, but also many ways to shoot yourself in the foot and have incoherencies or breaking your code because you just import something and you did not realize you were importing some instances in some cases. So, well, instance resolution, I feel, is still a hard problem. Not only it is a hard problem, but even the idea that we should have one instance per type is not totally obvious. So, for example, if you have a monoid of int, there's not really a canonical monoid of int, right? Because there are many ways to define valid monoid of ints. You can say, okay, sum is a valid monoid of ints, product, max, mean, first, last. All of those are quite valid, right? The other thing is that in Haskell, you have those functions like num, delete, union, group by, that expect a specific equality or odd constraint. But many times you want to have a specific constraint because in your code, you want to have a specific meaning for equality or a specific meaning for ordering. You want to group things differently. And it's pretty tedious to have to create a new type just to be able to do those operations. So that's why now in Haskell, we have those operations are duplicated by having num by, delete by, union by, where you can pass specific functions according to your context. So there was this nice proposal 2 years ago, which is even implemented in a prototype version of GHC, where we want to open even more of the type class resolution and type class mechanisms to the end user. So the idea is to make the dictionaries accessible to users. And every time you have a type class like EQ, you will have a corresponding data type like EQ.dict, giving you access to the function inside the type class. And you should have a way to build those dictionaries using Haskell, not using instance declarations. So on the fly, you can build a new dictionary, for example, reversing the order for a given type. And once you have a dictionary, you should be able to apply it to a function that's expecting a given type class. So you should be able to say at and pass a specific dictionary, a bit like you would do type application. Now you do dictionary application. And so that gives actually a lots of flexibility, and that solves lots of different problems related to type classes. But of course, the same question arises, which is, okay, is it safe to do so? Aren't we going to run into problems related to inserting elements in the set and so on? And it turns out that it's actually safe to do so. So I really encourage you to have a look at the whole article or the presentation. There's the video online, but I can give you in a gist the reason why it's safe to do so. It's because the translation between a dictionary application and Haskell code is done by the introduction of a new type behind the covers, and like W in that case, and coercions between A and W of A. And it turns out that the mechanism for coercing types introduces a notion of role for types and role for new types. And if you look at the literature about coercions, you will see that some types have a representational role and sometimes have a nominal role. And when you do explicit application of dictionaries, you insist on the fact that the type A must have a representational role. And it turns out that in an operation like insert, you will not be able to do that because the way the insert function is built, the type is nominal. It's not representational anymore. So this will work. This is why there's a proof that this will be coherent. So that's nice. I'm really looking forward to this being added to GHC proper. So to recap, we need ways to wire some codes. Type classes are a very well-known way of doing this. And at the same time, using type classes creates all sorts of challenges and problems. So it's in a way, it's one point in the design space of how we assemble code. So it's also worth wondering, do we need type classes to do what we want to do? And there's this famous blog post by Gabriel Gonzalez about, okay, let's get rid of type classes. We don't need them actually to do some simple stuff. They might be more troublesome than they are worth. And then you have some people saying, okay, maybe we can build applications without using MTL, without using anything complicated like that, using something called the handle pattern, or sorry, that's too fast, the service pattern. So today I want to present this approach because I think it's a very nice approach to building Haskell applications. It's very easy to use, and it's very easy to get started and not being bogged down into difficulties with type inference, with effect systems and hierarchy types and stuff that can be too complicated. So the idea is to just declare components using records of functions. So you want to do some logging, you put 2 logging functions into a data type, and that's going to be your interface. And you have this clean difference between an interface and an implementation, which is what we want when we build systems. And then you have a constructor function that's going to give you the way to build a component like this. And this constructor function can take other components as dependencies. And then it's really nice because you can use some Haskell syntactic tricks if you want to make this pretty concise. So you can use record wildcards, that's the 2 dots here, to inject the info and error functions in the logging component. And also because you have a where clause, you know that the time component as a dependency will be accessible to both info and error. So you don't have to pass parameters around. They are kind of accessible to the whole component. And I mean, if you come from Scala and you look at this code, you will say, oh, this looks pretty much like a case class to me. It's very, very similar. And once you have this, I mean, you have components, but you still need to wire them. And wiring the code is kind of tedious. And at the same time, again, it comes back to the Lambda abstraction problem. Once it's wired, you cannot change it. So the way to get around this is to have another record of functions where you put all your constructors inside. And you use this, to build your application, and you wire things only once. And then if you want to rewire stuff for tests, you can just override parts of your wiring. And you can say explicitly, okay, actually, I don't want to log anything. And then this new logging prime function is the one that's used to wire all your application. So that means you can rebuild your whole application with no logging at all. So this is a very flexible way of building applications, and this has the nice property that you can override very easily dependencies like this. Of course, it has some limitations. So one limitation is that the wiring, again, now is very manual. You have to do it once, at least yourself. And it's kind of a shame because most of the time, if you look at the definition of all the constructors, they already tell you the whole story. You can just by following the types, you know how to build the application. And this is generally what type classes give you. Looking at the types, you can infer how you can recursively build everything. It's also not extensible. If you put this application into a larger application, you will have to have a larger configuration, embedding the smaller one. You have to delegate some operations from the larger one to the smaller one. So it misses an extensibility story here. It's a bit sensitive to changes as well, because you need to specify those constructor functions with all their parameters. And if you override one of them, you're going generally to put some underscores because you don't care about the dependencies. And then that means that if you add one more dependency, you have to add one more underscore in all the places where you've tried to override that function. So it's not so nice. And finally, you can only have in your graph of components one instance per type. And to me, it's kind of annoying because I would love to have the flexibility to have several instances, even for the same type, into the same graph. And this is about the context we want to use a given component in. For example, if you have a layered application like this, you might want to have two components that have exactly the same type, but that are maybe configured differently. They might ping different servers. They might have some different configurations for the number of messages they accept per second or stuff like that, even if they have the same type. And it should be very easy to say this, to declare this. But you cannot do this with the previous technique. On the other hand, you can do this with a library called registry, which is kind of the same approach, but on steroids, because now we go back to doing a bit of metaprogramming. So type classes are in a way doing a bit of metaprogramming. You let the compiler create some code for you. Registry does a bit of the same. So you still have these ways to construct your components, and you put all of this in a sort of list that is now an extensible list. So for example, you can declare all your components like this, and you put that in a list of components. You can declare all the small configuration parameters in another list as pure values. You're not constructing anything. And then you have a registry of functions and values you can use to build stuff. And you can say, okay, now can you make an app out of this? And now it's doing the thing that's kind of obvious, is following the types. So if you want to build an app, what do? You look at the new app constructor, it's in there, it returns an app, but maybe it needs some other components. So you look at each of those other components, can you build them? You need an API, you need an HTTP component, and so on. So recursively, it's going to build everything by just going through the lists of everything that has been registered before. And then it's very easy to override stuff if you want to test your application. So since the algorithm is very simple, it goes through the list until it finds a suitable type. If you want to inject a new component to do no logging, you just put it on top of the list, and that's the one that's going to be taken. And because it's also an algorithm that's built as a Haskell library, there are ways to tweak this algorithm exposed to the library user. So you can say, in this context, if you are trying to follow those types, you can put this specific instance. Whereas in this other context of my application, if you are following those types, use this other instance. So it's quite flexible. And also because everything is kind of reified, now you're using metaprogramming to apply functions to each other and so on. You can also explore this thing as a data structure. So you can represent your whole application in a graph like this, which is not something you can do if you have purely some Haskell code. And actually, it's not something you can do even when you're using type classes and instances. There's no way to extract all those dependencies between instances. And sometimes it would be nice to be able to see that kind of graph with instances depending on each other. So this is kind of nice because now we are using a bit of metaprogramming, going outside of the language to do stuff, useful stuff for us, reducing boilerplate, but it has some limitations. So you cannot put everything into a registry because it's using the typeable and dynamic libraries in Haskell. You can only put simple types. Also, you can choose between having errors at compile time or at runtime. So errors at compile time are a bit more terse. It's using things like type families and so on. So the error messages might not be so nice in telling you that it cannot build something. Or you can have some more explicit explanation of what's going on. If you cannot build a given type at runtime, it will show you the full registry. It will tell you what it was looking for and so on. But then, well, it's at runtime, so it's not so nice to have things blow up in your face at runtime. And it has also the drawback that it's kind of a centralized access. So you build a registry, and everywhere you need it, you have to pass it around. You have to import it. Whereas type classes are kind of global instances. Whenever the compiler thinks it needs an instance related to a type, it knows where to find it. You don't specifically need to import everything in a given file to get access to those instances. And finally, it's also a small DSL. So it's, as you can see, there are things you need to learn how to create a registry, how to use it, how to tweak it. So it's an unfamiliar way of wiring applications, and you might not like it because it's kind of magic in a way. So can we do anything better? Are the alternatives just doing things using the compiler, using type classes, and trying to expose things from the compiler through language pragmas? Or should we do everything manually, injecting our dictionaries manually, maybe using a bit of metaprogramming to do some of the things with some metaprogramming, reducing some boilerplate? Or maybe is the problem with just Lambda abstraction in the beginning? You know, the Lambda abstraction, Lambdas are kind of closed forms. You cannot change them. So today I want to present you a different way of computing, which is the tree calculus. So there are other ways than the Lambda calculus to compute stuff. And the tree calculus has been invented by Barry J. He's still working on it. And for many, many years, he's been working on different calculi. And one of them is the pattern calculus, for example. And there's a book on the pattern calculus. And the tree calculus is taking lots of inspiration from the pattern calculus. So what is a program in the tree calculus? So in the tree calculus, programs are just binary trees. It's very simple structure. It's unlabeled binary trees. So this is a program, and we will see later on what it is precisely. So what can we do with binary trees? Well, there are just 3 evaluation rules that you can use to apply trees to other trees and do computations. So the first rule says something like this. You can take, for example, a tree with 2 nodes that has a subtree Y, and now you want to apply it to a new tree Z. And the first rule says, if you are in that situation that the tree on the left has just 1 leaf, then you can forget about the Z, and it will just return the Y subtree. And if you look at what's just going on here, it's kind of the const function, right? So you can call this tree with just 2 nodes, the const operator. It's always going to return, if you pass it 2 arguments, it's going to return the first one. So now let's see something a bit more complicated. Now you have a tree with 5 nodes, and you try to apply it a new tree Z on this tree with 5 nodes. So in that case, the second rule is going to fire, because the second rule says, if on the left you have a node with just 1 branch, now that will create 2 trees applied to each other. So that would create the following situation. But that's a situation we had on the previous slide of the const operator, where we ignore the tree on the right side and we are just left with Z. So effectively, a tree with just 5 nodes here, where you pass a Z, returning a Z, that's the identity operator. So now we have a const operator, the identity operator, and you can build more operators out of this, and I must say more combinators. So if you're a bit familiar with the SKI calculus, so it's a way of computing with pure combinators. There's no notion of variables. And with just two combinators, SK, you can effectively have all the power of the Lambda calculus. And the first tree I showed at the beginning was the S combinator implemented as a tree with those rules. So maybe you want to be a bit more convinced that you can do everything you can do with the Lambda calculus with just trees. And it turns out that if you decide that the K const operator, if you call it K, and if you call the identity operator I, and you decide that K is true and Ki is false, then you can define Boolean operations, and you can have trees doing N, or, implies, and so on. You can also define natural numbers. So if you say that K apply repeatedly N times to a leaf is a natural number N, then you can have combinations for checking if a given tree is 0 or not. And that's given on the slide here. So you can have operations on natural numbers. You can even have recursion. So if you know about the Y combinator is a way to apply a function repeatedly to itself. So you can, Y of F is going to be F of Y of F, that's going to be F of Y of F, which in a way creates a problem, because how can you stop infinite recursion into this? And there's a very clever trick in the tree calculus. So you can define a wait construct where you will wait for applying two things together. You will wait until you get a new argument and then apply stuff. So the Y2 of F will not expand until you apply an X to it. And this is how you can represent recursion with just one tree. But you can do more. I mean, you can now also inspect trees. And that's thanks to the third rule. You can go inside trees and see what they are composed of. And that's really important, because now you can say something is a leaf, a stem, or a fork. And that means that you have full reflexivity. So you can write inside your language a program like size, which can inspect a program and find out about its size. You can recurse with Y2, check if something is a stem, use arithmetic and natural numbers, use a plus operation, and eventually compute the size of a program. You can even have a self-evaluator, a program evaluating other programs using some branch first rules. And you can do more. In particular, you can tag nodes with some tags that are not going to be problematic when you apply values to functions. So you can still have a tagged tree that can still do applications. And what that means is that you can build type systems on top of that. So it's very early days to see how this is going to evolve. But you can totally imagine that you can have programs, type checking nodes, putting some tags corresponding to types, checking that types can be coherent, and finding out, doing all the classical type algorithms that we know to find out about the types for some terms. Which means, and this is why I've been really interested in this new calculus, because that opens all sorts of possibilities. And for what interests us today, that means that you can recursively explore programs, but this time you don't have to use the compiler to do this. You don't have to use type classes or Cabal or some meta-programming to do this. You stay inside the language to do this, the thing you could not do before. Now you can peek behind the Lambda to understand exactly how it's built. And since you have access to types, you can have a look at your application, recursively explore it, and replace all the components of a given type. And you don't have to use meta-programming. You can use the same language potentially to do this, to graph the parts that you want and rewrite your programs. So I think this has tremendous applications for kind of dependency injection, type classes, but actually even more, because if you think at all the performance optimizations we can have using staging, for example, or using programs that are going to rewrite themselves at runtime once they have more data and so on, that opens all sorts of possibilities that are very, very exciting. So it's very early. There are still lots of developments to do about district calculus, but I hope that I sparked your curiosity about that, and that I incite you to have more exploration around the Lambda calculus and other forms of calculi out there. So yeah, that's all for my talk today. I hope you enjoyed it.
Oh, thank you. Thank you. It's been an eye opener for me, and yeah, you did spark my curiosity. If you want to see if you sparked the curiosity of others, then please join the QA room. I'm sending a link on the chat.
Thank you. I'm going there right now.
Please do, and thanks once again. Brilliant talk.
Thank you.